Hello everyone and welcome back once again to the online lectures of design of pre-stressed concrete through JCE Connect. So in today's session I am going to solve one more problem over the design of end block. Okay, so it's a similar type of problem what I have solved in the previous session. So same steps you have to follow here in this session. So I'll read out the problem here. The end block of PSC beam rectangular in section. The end block of PSC beam is a rectangular section, that is 150 mm by 400 mm, and an effective pre-stressing force of 400 kN is transmitted to the concrete by plate size of 150 mm wide and 120 mm deep, concentrically located. So again the cable is concentrically located at an ends. Calculate the reinforcement for the end block for maximum transverse tension. Sketch the reinforcement details. Use Fe4 and first steel. So here it is given as, so again the rectangular, so the PSC beam is a rectangular cross section of 150 mm and 400 mm, 150 mm width, 400 mm deep, and this beam is carrying a pre-stressing force of 400 kN, is transmitted to the concrete by plate, that is anchorage plate of size 150 mm wide and 120 mm deep, and again it is concentrically located at the ends. So we have to find out the reinforcement for the end block for maximum transverse tension. Sketch the reinforcement details. Use Fe4 and 5 steel. Okay, so this is regarding the we have here the beam is 150 mm wide, 400 mm deep, and the anchorage plate is, so this is a plate. Okay, it's a plate of 150 mm wide and 120 mm deep. Okay, and other given data are, they are given as the pre-stressing force P, it is given as 400 kN. The pre-stressing force P is given as 400 kN. Okay, and the size of plate is 120 mm deep, so therefore Yp naught is given as 120 mm. Yp naught is given as 120 mm. Okay, and as I told you, when it is concentrically located, so that times what will happen? So this will be, so here this distance is called as y1 and y1. Okay, so it is called as so you can say this from here to here and again from here to here is y1 and y1. So y0 is y1 plus y1. So as I discussed in the determination of yp0 and y0, so y0 is y1 plus y1. Okay, so that is nothing but y0 is 400 mm. Okay, y naught is 400 mm. Okay, so we got yp naught, that is plate, and this is for bearing y naught, sorry, the prism. Okay, then after that, now first of all we have to find out the bursting force. Now bursting force is given by FBST is equal to P to bracket of 0.32 minus 0.3 by P naught upon y naught. Okay, 0.32 minus 0.3 into yp naught upon y naught. Okay, so here the P is given as 400 kilonewton into bracket of 0.32 minus 0.3 into bracket of yp naught is 120 and y naught is 400 mm. Okay, so yp naught is 120 and y naught is 400. Okay, so after calculation we'll get FBST is equal to, this will get it as 92 into 10 raised to 3 Newton. We get it as 92 into 10 raised to 3 Newton. Okay, so we'll got FBST. Then after that, so therefore, so next area of steel is given by FBST is equal to 0.87 Fy AST. FBST is equal to 0.87 Fy AST. So therefore AST is equal to FBST divided by 0.87 Fy. So again assuming Fe 415 steel. Okay, assuming Fe 415 steel, so I can write here, assume Fe 415 steel, assume Fe 415 steel. Okay, so therefore AST is equal to, we will get it as FBST is equal to 90 into 10 raised to 3 divided by 0.87 into Fy as 415. So we will get AST is equal to 254.81 mm square. So we will get AST is equal to, we'll check here, so 92 now, this is 92, 92 92 into 10 raised to 3 okay, so we got 254.81 mm square. Okay, now again you have to assume the diameter. Okay, So here assuming 10 dia bars, assuming 10 dia bars, so therefore number of bars is equal to 254.81 divided by pi by 4 into 10 square. So okay, so here we'll get it as 3.24 numbers. We get it as 3.24 numbers. Okay, so but I told you it should be the addition of 3, 6 and 9. Okay, so we'll say 6 bars. Okay, we'll say 6 bars in each direction. 6 bars in each direction perpendicular to each other. Okay, so we'll draw the sketch here now very quickly. Okay, so first of all, the size of the beam, it is like this. So therefore now the bars are like, we have to provide 6 bars, so we'll have 2 bars. We'll have 2 bars, that is vertical and horizontal. So 1 2 1 2 1 2, so 6 bars horizontal and 2 2 2, 6 bars vertical again. Okay, so the zone will start distance of 0.1 y0, and the total, the length of the zone we have to design for 2 y0. Okay, that is y1 plus y1. 2 y0 is nothing but, or y0 is nothing but y1 plus y1. Okay, so here, so sorry, this is y0, we can call it as y0. Y0 is equal to y1 plus y1. Okay, and if I want to show in the elevation how the bars will be, so 2 bars vertical, and we have 2 bars horizontal like this. Understood? So that is, you can see that 2 bars verticals plus 2 bars horizontals, so total 6 bars. 2 4 6 vertical and even horizontal 2, then next mesh 4, again the third mesh is 6. Understood? So this is regarding the calculation of the busting tensile force and the reinforcement detailing. Okay, so now we'll solve one more problem, okay, with a cable profile, change in cable profile. Okay, so it is given like the end block of pre-stressed beam 250 mm wide and 500 mm deep. The section is pre-stressed by 2 cables. So this is important now, 2 cables carrying a force of 450 kN. First cable is parabolic and located at a 125 mm below the center line. CL is center line at the center span of 10 meter, so the span of the beam is 10 meter, and anchored at end point 125 mm above the center line. So the cable profile, the first cable is parabolic. So with the eccentricity at center of the span is 125 mm below the center line, and at end 125 mm above the center line. Okay, then the second cable is straight. Okay, so the second cable is straight at a E is equal to 100 mm from the bottom of the beam. So again the second cable is straight, it is not parabolic, with the eccentricity 100 mm from the bottom of the beam. The distribution plates, nothing but the anchorage plates for cable are 100 mm deep and 250 mm wide. Okay, so the plates are used as 100 mm deep and 250 mm wide. Okay, understood? So calculate the maximum tensile stress along the axis of the beam using IS code. So you have to find out the maximum tensile stress along the axis of beam using IS code. Okay, so understood? So this is the given the sketch, not given, as per the this thing. So the beam is 250 mm wide by 500 mm deep, and with two cables. We can see one green color, one more the yellow color. Okay, we have two cables. The first cable is parabolic with a distance 120 mm below from the center line at mid span or a center, and 125 mm above at end. Okay, so that is first cable. The second cable is straight, okay, with eccentricity 100 mm from the bottom. Understood? So then here we have the plates. The plate they are given as it is 100 mm in depth, so the plate is 100 mm in depth and 250 mm wide. So same here for the two different plates for two different cable profiles. Okay, so now, so because they are given as the directly the size of the plate as 100 mm, so therefore I can write yp naught is equal to 100 mm. Yp naught is equal to 100 mm. Understood? Then for the calculation of y naught, the calculation of y naught. So here we can have the stress distribution through the plates. This plate is located at a distance of 125 mm, 125 mm from the center to the above. Okay, तो यहाँ पे क्या होगा? So from here to here it is y1, then again from here to here it will become y1 plus y1. Understood? I told you in case of the eccentric plates what you have to do. So here, so this is the cable we have, and this distance is 125 mm. Okay, this distance is 125 mm. So 125 plus 125, so that is 250. Obviously, because the center line is also 250. This is also 250 because the depth of the section is 500 mm. Okay, so 125 plus 125, 250. And for cable 2 it is 100 mm. Okay, so this will be again y1 plus y1. So this is y1, one more y1. Okay, I told you no, you have to make it double. So y1 plus y1, that is 200 mm. So for cable 1 the y naught is 250, and for cable 2 the y naught is 200. Okay, so this is the detail required for to understand how to get the value of y naught. Okay, understood ना? अभी हमारा केबल का सेंटर है यहाँ से 125 है, तो इसको डबल करो. I told you ना, you have to make it double. तो 125 plus 125, 250 हुआ, which is again center of the section because the total depth is 500. For cable 2, this is 100, so you have to make it double, so 100 plus 100, 200. Understood? So now we'll proceed for the calculation. Okay. So we have to calculate for individual cable here now, for individual cable. Okay. So cable 1, for cable 1, for cable 1, for cable 1. The YP naught is already we know, that is 100 mm. And next the Y naught, that is Y1 plus Y1, that is 125 plus 125, so Y naught will get it as 250 mm. Y naught will get it as 250 mm. Okay. So now you have to find out the tensile stress. They are asked to calculate maximum tensile stress. Okay. Now the maximum tensile stress is given by Fv max is equal to Fc into bracket of 0.98 minus 0.825 Yp naught upon Y naught, bracket complete, Yp naught upon Y naught. Okay. So where Fc is equal to the direct stress P divided by Y naught into Y naught, that is area of prism. So so it is P is 450 into 10⁻³ divided by 250 into 250. Okay. So that Fc is given by P divided by area of prism. Area of prism is Y naught into Y naught. Understood? So therefore we'll get Fc is equal to 7.2 Newton per mm square. So therefore Fv max is equal to 7.2 bracket of 0.98 minus 0.825 into bracket of 100 divided by 250. So we'll get this value as 4.08 Newton per mm square. Okay, so we'll get this value as 4.68 Newton per mm square. Now for cable 2, so we have calculated for cable 1. So for cable 1, okay. Now for cable 2, so here also the plate size is same, so therefore Yp naught is 100 mm and Y naught is again y1 plus y1. So it is given as 100 mm from the bottom, so that is y1. So 100 plus 100, so this has 200 mm. 100 plus 100 is 200 mm. Okay, that is y0. So again you have to find out same FV max, that is FC. So where again, so now, so we'll calculate FC first. Now FC is equal to P divided by 100 into y naught. So P is 450 into 10 raised to 3, okay, into, that is 200 by 200 mm. So get the value of FC is equal to 11.25 Newton per mm square. So therefore tensile stress FV max is given by, again, FC into bracket of 0.98 minus 0.825 yp naught upon y naught, bracket complete. So FC we have got it as 11.25 into 0.98 minus 0.825, yp naught is 100, but y naught is 200. So we'll get this as 6.38 Newton per m square. So we got the tensile stresses. The maximum tensile stresses when the cable is parabolic, that is 4.68, and when the cable is stretched, that is 6.38. Means we can conclude that the concrete or the section will be more strong or capable than when the cable is straight. When the cable is parabolic, so it can resist more stresses compared to straight cable, because straight cable we have got it as 6.38, it can develop a maximum tensile stress of 6.38, but same cable if I provide it in a parabolic form, it can take only 4.68. so there is a hike here when you provide straight cable, but there is a reduction when you provide the profile of the cable as parabolic. Understood? So this is the calculation for the given problem. Okay, thank you.